Look at the stars scattered across the dark canvas of the universe. They seem peaceful, burning quietly in the endless void of space. But as we have learned in our previous journeys, the death of a star is anything but peaceful. It is a cataclysmic event that forces the fundamental laws of physics to their absolute breaking point. We know that when a star of unimaginable size runs out of fuel, its core collapses under its own crushing weight, tearing a hole in reality to create a black hole. But what happens to the stars that are slightly smaller? What happens to the stars that are massive, but not quite massive enough to break the universe completely? They do not fade away into the dark. Instead, they freeze in a state of perpetual, terrifying extremity. They become the densest, most magnetic, and most dangerous physical objects in the observable cosmos. Today, we are traveling into the heart of dead stars. Neutron stars. To understand how a neutron star is born, we must witness a supernova. When a star with a mass of roughly 10 to 20 times that of our Sun reaches the end of its life, its iron core collapses inward at a significant fraction of the speed of light. The outer layers of the star bounce off this collapsing core, creating an explosion so violently bright that it can outshine an entire galaxy of 100 billion stars. But while the outer shell is blasted into the cosmos, the core is crushed. Gravity pushes inward with such terrifying force that it overwhelms the electromagnetic repulsion holding atoms apart. The empty space inside the atoms is completely erased. The negatively charged electrons are violently smashed into the positively charged protons. They fuse together, neutralizing each other, creating a solid sphere made entirely of neutrons. The collapse stops. The newborn neutron star stabilizes, held together by a quantum mechanical principle known as neutron degeneracy pressure. But the scale of what has just happened is almost impossible to comprehend. An object with a mass 1.5 times greater than our entire Sun has been crushed into a sphere no larger than 20 kilometers across. Extreme density. To put this density into perspective, if you could somehow extract a single cubic centimeter of material from the core of a neutron star, it would weigh roughly 1 billion metric tons. That is the equivalent of taking a massive asteroid and compressing it into the size of a sugar cube. Because of this incomprehensible density, the gravitational pull on the surface of a neutron star is 200 billion times stronger than what we consider normal. If you were to drop an object from a height of just 1 meter above the surface of a neutron star, it would hit the ground in a fraction of a microsecond, accelerating to over 7 million kilometers per hour before impact. This extreme gravity also creates the smoothest physical objects in the universe. A neutron star has a solid crust composed of hyper-compressed iron nuclei arranged in a perfect crystalline lattice. But because the gravity is so overpowering, any imperfections on the surface are instantly crushed flat. The maximum height of any mountain or elevation on a neutron star can be no larger than a few millimeters. It is a perfectly smooth, perfectly spherical mirror of dead iron, glowing with intense residual heat. A perfect sphere. But a neutron star is not just a heavy, smooth rock. When the original giant star collapsed, it did not lose its rotational energy. Just as a spinning figure skater spins faster when they pull their arms in, the collapsing star conserves its angular momentum. A star that used to take weeks to rotate once is crushed down to the size of a city. and its rotation speeds up exponentially. A newly born neutron star can spin on its axis up to 700 times every single second. As it spins at these mind-bending speeds, it generates a magnetic field trillions of times stronger than anything we can measure. This magnetic field channels highly energetic radiation and accelerating particles toward the magnetic poles of the star. These particles are violently blasted out into the cosmos as twin beams of blinding radiation. If these beams happen to point in our direction as the star rapidly spins, our telescopes detect a perfect rhythmic pulse of light. Pulsars. We call these specific, rapidly spinning neutron stars pulsars. They are the cosmic lighthouses of the universe. Their rotation is so incredibly precise, ticking hundreds of times a second without losing a fraction of a millisecond, that they are actually more accurate than the most advanced atomic clocks ever built. But not all neutron stars become pulsars. A very small percentage of them go down a different, much darker path. They become an entirely different class of monster. Magnetars. If a neutron star forms with a specific spin rate and internal temperature, a chaotic dynamo effect occurs within its core. This effect amplifies the magnetic field to levels that defy logic. A magnetar is a neutron star with a magnetic field 1,000 times stronger than a standard pulsar, and 1 quadrillion times stronger than the magnetic field of our own planet. Magnetars are the undisputed magnetic champions of the cosmos. Their magnetic fields are so violently powerful that they actually distort the shape of the atoms nearby, stretching them into long, thin needles. If a spaceship were to approach within 100,000 kilometers of a magnetar, the sheer strength of the magnetic field would rip the electrons straight out of the atoms of the ship. The metal hull, the computers, and the very molecular structure of the vessel would simply dissolve into subatomic dust long before it ever reached the surface. But the most terrifying aspect of a magnetar is its instability. The intense magnetic field is locked into the solid, hyper-dense iron crust of the star. As the magnetic field shifts and twists, it puts unimaginable physical stress on the crust. Eventually, the crust cracks. Starquakes. This event is known as a starquake. When the crust of a magnetar fractures by even a single millimeter, the sudden release of magnetic energy is catastrophic. In the year 2004, satellites detected a blast of gamma radiation from a starquake on a magnetar located 50,000 light-years away. For a fraction of a second, that single invisible blast delivered more energy to our solar system than the Sun does in 250,000 years. It temporarily ionized the upper atmosphere of our planet from halfway across the galaxy. But the deepest mystery of a neutron star lies even further down. What exists beneath the iron crust? What happens at the absolute, dead center of the star, where the pressure reaches the mathematical limit of the physical universe? Astrophysicists theorize that deep in the core, the pressure is so immense that even neutrons cannot survive. They are crushed open, dissolving into their fundamental building blocks. Quarks. Normally, quarks are always bound together, but in the core of a neutron star, they are squeezed into a free-flowing, ultra-dense fluid known as quark-gluon plasma. And in this extreme environment, a bizarre and terrifying transformation might occur. Some of the standard up and down quarks might be crushed into a heavier, completely unnatural state called a strange quark. Strange matter. If enough strange quarks form, they combine to create strange matter. Strange matter is theorized to be the most perfectly stable substance in the universe. It is completely indestructible, perfectly dense, and absolutely flawless. And that perfection makes it incredibly dangerous. Because strange matter is so perfectly stable, it wants everything else to be stable too. If a particle of strange matter comes into contact with normal atomic matter, it instantly converts that normal matter into more strange matter. If the core of a neutron star turns into strange matter, it consumes the entire star from the inside out, turning it into a strange star. But the true danger arises when two neutron stars collide in a catastrophic cosmic event known as a kilonova. When these ultra-dense stars smash into each other, they release a shock wave of gravitational energy and forge the heaviest elements in the universe, casting clouds of pure gold and platinum into the void. But during this violent collision, tiny droplets of strange matter might be flung out into the darkness of space. These microscopic droplets are called strangelets. Strangelets, the perfect infection. A strangelet might be smaller than a grain of sand, but it is infinitely heavy and indestructible. It drifts through the freezing vacuum of space for billions of years, completely undetectable. If a strangelet were to eventually collide with another star or a wandering planet, the results would be apocalyptic. The moment the strangelet touches normal matter, the infection begins. It converts the atoms of the star into strange matter, releasing a burst of heat and energy, which converts more atoms, creating a runaway chain reaction. Within a matter of hours or days, an entire star would be consumed, shrinking rapidly and collapsing into a dark, dead sphere of pure, strange matter. Is the universe filled with invisible, drifting strangelets, silently waiting in the dark to consume stars and planets? As of today, it is only a mathematical theory. Our telescopes have not yet detected a confirmed strange star. But neutron stars and magnetars are very real. They are the glowing, spinning graves of massive stars. They are cosmic engines of extreme gravity, blinding radiation, and impossible magnetism. They stand as a testament to the fact that when stars die, they do not go quietly. They leave behind monsters that shape the very fabric of the cosmos. If you want to continue exploring the terrifying and beautiful extremes of the universe, hit the like button and make sure to subscribe. Our journey into the dark is far from over. And as always, keep looking up.